In this video, we will solve a problem related to projectile motion. So here's the problem we're given. A projectile is fired from the ground at an angle of 60 degrees upward, and it lands 25 meters away, and we have to figure out what speed was the projectile fired at initially. So there's a bit of a long process to figuring this problem out. So I want to first outline what we're doing so that we don't get lost along the way and we remember sort of where we're headed and why we're doing what we're doing. So the first thing we'll do is find the position function. In other words, the first thing to do is just figure out what the equation is for the motion of the projectile. 2. We'll find when does it hit the ground. In other words, what time, what value of t does the projectile land? And then the last thing we'll do is we'll take our answer from part 2, we'll plug in our value of t from part 2, so we'll call our position function r. We'll plug our answer to part 2 into our answer from part 1, and set that equal to 25. When I say set equal, I mean set just the x component equal. So this is the general outline of what we're going to do. So first, let's do part 1. First, let's just find the position function. But even before that, let's draw a picture and look at what we're being asked to find. So let's pretend that where the projectile is fired from is the origin, point 0, 0. And here's the point where it lands. And the projectile moves in some arc like this. And so here's like our initial velocity vector. So we'll say v for velocity. This is v of 0, the initial velocity. And this distance will be 25 meters, as we were told at the beginning. It lands 25 meters away. Okay. So let's call S the initial speed. This is really what we want to find. Once we know S, this will be our final answer at the very end of the problem. So using the notation from my picture, this is also the same thing as the norm of the vector v of 0. Alright, using basic trigonometry, v of 0 is, since we are told that this angle right here is 60 degrees, which is pi over 3, v of 0 is s times the cosine of pi over 3, and s times the sine of pi over 3. So we can factor the s out. This is 1/2 square root of 3 over 2. We can even factor out 1/2. This is s over 2 times the vector 1 root 3. Okay. Now we're still on part 1 here. We want to find the position function. So the starting point is to use the acceleration. Now, as you maybe learned in a physics class at some point, the acceleration due to gravity is constant. So even though we're writing this as a function of t, it should not actually depend on t. It's constant. It's always the same. And it points down. So there's no x component. And we're simplifying everything here as two-dimensional, so there's just going to be x and y. So it only has a y component, and it points down, so it should be negative. And I'm just going to call it g for gravity. So this is what you've probably seen before, is estimated as 9.8 meters per second, but we're just going to leave it as g here to keep things simple. So that's the acceleration. Now to get the velocity, of course we integrate. So we take the integral of the acceleration, and we get the initial velocity plus t times the vector from before. And if we combine that with our v of 0 from above, this is s over 2 plus 0, comma, square root of 3 over 2 times s minus g times t. Now finally we have to integrate one more time. So the position is the integral of velocity. Again, we integrate our answer from above. And our initial position is 0, 0, so we won't have any constants of integration. It'll just be 0. So here we get s over 2 times t for the x component, and for the y component we get square root of 3 over 2 s times t minus g over 2 t squared. Okay, so this is our position function. So we're done with step 1. Now remember what I said we're going to do. Step 2, we're going to find when does it hit the ground. So step 2. In other words, when is the y coordinate 0? Right? That's when it hits the ground, is when the y coordinate is 0. So let's just take the y coordinate from our position function and set it equal to 0. And we can factor the left-hand side. There's a 1/2 in both terms, and there's a t in both terms. So we can factor out a t over 2. And here get square root of 3 times s minus gt. So we get two answers. One answer is when t equals 0. So we get two solutions. One solution from the first factor is when t equals 0, but that doesn't help us. We already knew that y was 0 when t was 0. That's just because it was fired from the ground. But our second solution is when the thing in parentheses is 0. And now we can solve this for t. So this is square root of 3s over g. So we're done with part 2. We found when it hits the ground. assuming that we knew s, which we don't yet. But if we did know s, this would be the time when it hit the ground. Okay, on to step 3. Step 3, we want to take our previous answer and plug it in. So here's our position function, and we want to plug in this time. This is when it should hit the ground. So we want to plug in t is square root of 3s over g into our function r. So let's see, what do we get? If we plug that in, we get, in the x slot, we get square root of 3 over 2g times s squared. And in the y slot, we should get 0. Right? Because how we found this number, this value of t, it was exactly the time when the y-coordinate should be 0. So let's not even bother plugging it in. It should be 0 if we did everything right so far. And now we're almost done. So this is telling us, this is the position when it hits the ground. And we were told at the beginning that it hits the ground 25 meters away. So the final thing we need to do is say, if it hits the ground 25 meters away from where I started, then this number here should be equal to 25. And now we can finally solve for s. So, square root of 3 over 2g times s squared should be equal to 25. And now just do a little simple algebra, and we get our final answer. S is the square root of 50 over the square root of 3 times g. And this is the speed that the projectile was fired at in the very beginning.